Okay, ladies and gentlemen, thank you for coming, or thank you for remaining, for those who did remain. The press conference we have today, again, it's on what we're calling the Arctic Methane Emergency. Our host for this press conference is the United Planet Faith and Science Initiative, and that is also being sponsored by the Abibimman Foundation from Africa and the Interfaith Center for Sustainable Development in Jerusalem. And today, the UPFSI will focus on the science aspect. Now, my name is Stuart Scott, and I'm the founder of the United Planet Faith and Science Initiative. I'm also a member of an organization known as the Arctic Methane Emergency Group. If you want to find it on the internet, it's AMEG, ameg.me. I'm also the Deputy Director General of an NGO called ESCO, the International Ecological Safety Collaborative Organization. Now, I want to show you a bit from the New York Times online that appeared on November 30th, just to underscore. I don't know if you in this audience need the underscoring, but out there in the rest of the world, we still need some underscoring. In particular, the second paragraph, even with a deal to stop the current rate of greenhouse gas emissions, scientists warn the world will become increasingly unpleasant. And the author goes on further to say, without a deal, they say, the world could eventually become uninhabitable for humans. To me, this is a milestone that the mainstream press is using that strong language. Now, before we hear from our speakers with us today, I wanted to set the tone by including a few words from Dr. Peter Wadhams. He's a professor of ocean physics at Cambridge University. He's head of the Polar Ocean Physics Group from Cambridge. He's been researching the Arctic ice cap, the Arctic ice pack, since the 1970s. He has over 300 peer-reviewed papers, and he's considered one of the world's foremost authorities on the conditions and physics of the Arctic sea ice. He's been going in nuclear submarines underneath the ice pack, aiming sonar upwards to see the thickness and estimate the dynamics of what's going on for many, many years. And here we will hear, in Dr. Wadham's own words, a few remarks about what the loss of Arctic sea ice portends for humanity.
At the moment, we have to rely on Shakova and Semiletov, who've been doing that work, and they have then expert knowledge of the seabed conditions, and they're the ones who are estimating the 50 gigatons. So that could be revised up or down if further work is done in that area.
And do you think civilization could survive a 50 gigaton release of methane?
No, I don't think it can. I think that if you look at the existing predictions of global warming rates, what's kind of eerie is the fact that the business as usual projections, even the cautious ones produced by IPCC, are still giving us about 4 degrees of warming by the end of the century, and with 2 degrees has been taken arbitrarily as the level beyond which nasty things happen. I don't know why it's 2 degrees, but that will be reached by the middle of the century, and 4 degrees by the end of the century. Now, 4 degrees, people who've calculated what that would do to food production, to die-off of forests, to acceleration of warming due to various extra feedbacks that kick in, that the general conclusion is pretty dire, that if you get to 4 degrees of warming, then collapse of civilization is what's going to happen, because the world won't be able to sustain anywhere near its present population. So the result will be chaos and warfare. So that's just the eerie thing is that that's predicted by the IPCC report, but the projection of warming by the end of the century is 4 degrees. But nowhere do they state at all that 4 degrees is a catastrophe for economically and socially for the planet. And now with this Arctic methane, you're simply adding another element to the warming, even if it's only an extra 0.6. That brings forward the date at which catastrophic warming is achieved by maybe 20 years.
What we're dealing with here, in my humble opinion, is the gun going off. This is the element, that the wild card that portends, as Dr. Wadham says, the collapse of civilization on short order this century. This is something we have to deal with, and that's why we've brought these gentlemen here with us. Now, first, I'll introduce John Nissen, who spoke at length yesterday and will today just introduce our speaker, Paul Beckwith. John Nissen is the chairperson of the Arctic Methane Emergency Group.
Thank you very much, Stuart. Thank you very much. In our press conference yesterday, I told you the terrible truth about the Arctic, which our Arctic Methane Emergency Group has discovered. The Arctic sea ice disappearance presents an existential threat to civilization. That's making the planet uninhabitable. And that's far more immediate threat than the threat from CO2 emissions, which is a long-term threat. This fact about the sea ice is conspicuously absent from the IPCC AR5 reports. And Peter Wadhams and others think this is scandalous. The AR5 assessment does not even have a diagram to show the precipitous decline in September sea ice. Sea ice could disappear at the end of summer as soon as next September. At that point, further warming of the Arctic, sea level rise, methane release in that time bomb, and abrupt climate change could become unstoppable. The fuse will have been lit and will be going off very quickly. We consider it an absolute scandal, as I said, that IPCC says nothing about the greatest threat to humanity since civilization began. I'll say that again. We consider it an absolute scandal that IPCC says nothing about the greatest threat to humanity since civilization began. It is now so late in the day that only drastic intervention with geoengineering techniques have any chance to save the sea ice and prevent an unstoppable descent into total Arctic meltdown, climate chaos, methane time bomb going off, etc. Now, Paul,
John, I'm sorry.
Paul Beckwith will now tell you more about the colossal impact that Arctic warming is having already on climate change. And we will mention some techniques to deal with the longer-term problem of excess CO2 in the atmosphere. Thank you for listening.
I'm sorry, there was a bit of a crunch on time here, and so John went a little longer than we had expected. Let me introduce then Paul Beckwith, our next speaker, who will speak for a good period. He he's a professor at the University of Ottawa, and he teaches climatology, meteorology, and he researches abrupt climate change, past and present.
Thank you. So I'm going to give you a story today of the climate system. It's very important to look at the big picture, the overall climate system, not just elements like sea ice or atmosphere or forests, but the whole entire picture. So I'll try to do that in the time I have available. So we all know greenhouse gases are rapidly rising. However, the focus is almost exclusively on CO2 and other the greenhouse gases methane, CH4, and nitrous oxide, N2O, and N2O, are also very, very important and powerful greenhouse gases that on a molecule-for-molecule basis have much more impact on warming than does CO2. Now, there's also an emphasis on this 2 degrees Celsius. That's probably the term you'll hear more at this conference than anything else. 2 degrees Celsius is the threshold for dangerous consequences on the planet. But that metric, that measurement, is a bit misleading, whether it be 2 degrees or 1.5. What is crucial is the temperature distribution on the planet on a latitudinal basis mostly. So the equator is warm because it gets more solar intensity, and the poles are colder because they get less solar intensity, and the light intensity at the poles is weaker, so they're colder. So there's a temperature difference or a temperature gradient between the equator and the poles, and that changes with the seasons. Now, it's also changing rapidly now because of the Arctic temperature amplification. So the warming that we have thus far, the 0.8 or 0.85 degrees since the Industrial Revolution, has significantly changed the Arctic. In fact, the albedo or reflectivity of the Arctic region has decreased from 52% to 48% in 3 or 4 decades. So the Arctic is a lot darker. As a result, the Arctic is absorbing a lot more solar energy and is warming by itself at a much greater rate than anywhere else on the planet. In fact, on average, in the last number of decades, the Arctic temperatures have risen 1 degree Celsius per decade, whereas the global average temperature rises has been about 0.15. So that ratio is 6 or 7 times. So the Arctic is warming much faster. And that warming has even continued over the last 15 years when the global average temperatures have not risen as quickly as they were in previous decades because more energy is going into the oceans. So the sea ice in the Arctic is declining at an exponential rate downwards, and if that trend continues, will certainly be gone by the end of the summer in September before the end of this decade is out. So let's say that happens in 2020. The ice would be gone for probably a few weeks, maybe a month in September. The amount of energy required to melt 1 kilogram of ice is a certain amount of energy to melt 1 kilogram. When that ice is gone, that same amount of energy will heat the 0 degrees Celsius water from that melted ice by 80 degrees Celsius. So the Arctic snow and ice acts as a stabilizing factor on Arctic temperature. And when it is gone, then the Arctic temperatures will spiral upwards. So this is a problem for the methane and the decomposition of organic matter that is frozen in the permafrost on land and also in the marine sediments. And it's also a problem for the methane class rates, that lattice of water surrounding methane that is kept intact by temperature and pressures that are at the seafloor. But the water, for example, over the eastern Siberian Arctic shelf, which is a vast continental shelf off Russia, those marine sediments, the water above those marine sediments, it's about 50 meters deep, and it's warmed as much as 5 to 7 degrees Celsius in the summers. So it's warm enough to start melting, or to start percolating down and warming the marine sediments. And the Russian scientists have sent many expeditions there for 30, 40 years, and they're measuring a very large increase in methane coming up. Ground stations in Barrow and Svalbard are also measuring large increases in methane, and those act as ground truthing for satellite measurements. The AIRS satellite and the IASI satellite are measuring large increases of methane in the atmosphere above the Arctic. Now, on a short time scale, the global warming potential of methane is over 150 times, up to even 200 times that of CO2. That's on a few-year time scale, which is important as far as Arctic warming goes. On a 20-year time scale, that number drops to about 84 times. And the number always quoted in the press and in reports, including the IPCC report, is the 34 times global warming potential. But that's on a century time scale, which doesn't apply, obviously, to abrupt climate change. I'm talking about data. I'm not talking about models, okay? I mean, models tend to say it will take a long time for methane to come out of the sediments. It will take hundreds of years, perhaps, for the temperatures of the warm ocean above to go through, transmit through the sediments and melt the methane. But we're finding that fractures, imperfections in the seafloor, things like talics, which is unfrozen regions of methane, are weak points. We can't consider this as a slab, which is what the models do. So what is this doing? What this is doing is this Arctic warming that is so strong is affecting the atmospheric circulation and the ocean circulation of the entire planet. And this is happening today with 0.85 degrees of global average warming. And how it does this is, I told you that the equator, as you all know, the equator is warm, the poles are cold. Heat wants to move from warm areas to cold areas. So heat wants to move from the equator to the North Pole. It's deflected to the right by Coriolis force, which is due to the Earth rotation, and it forms the jet streams. So now that temperature difference is lower between those regions, there's less heat moving from the equator to the Arctic. So the jet streams slow down and become very wavy. Now, meteorologists all know the jet streams guide weather patterns. They guide storms. Because we're in a warmer planet, there's more evaporation from the oceans. There's more water vapor going up into the atmosphere, which then condenses into clouds. And when it condenses, it releases vast amounts of energy to fuel storms. So because there's more water vapor, there's 4% more water vapor in the last 30 years. We're changing everything. We've changed the chemistry of the atmosphere with the greenhouse gases. That's changed the water vapor, which affects the weather and climate. So basically, the jet streams become wavier. So you get very high ridges and very low troughs. In the ridges, it's very hot and humid air is coming up from the south. The jet stream acts as a wall between cold air northward and warm air southward. So in the troughs of the jet stream is where the storms occur. And the jet streams get stuck in place and cause these very unusual weather conditions. And also, as this wave moves, it causes extreme weather swings. For example, you can be in a location that can be plus 20 degrees Celsius one day. Within a few days, that temperature can be, daily high can be minus 20 degrees Celsius, and that's simply because the jet stream is very wavy and has moved past your region. So imagine the effects on the infrastructure, on roads and rails and buildings. And also the storms, when they do occur, they don't move as quickly because the jet stream is slower, so you get torrential rain events in one region and droughts in other regions. So this is happening now with our 0.85 degrees of warming. So obviously, these feedback effects are cascading feedback effects. And they can cause a vicious spiral of warming. So what do the historical records of our planet show the climate system being capable of doing in terms of warming? This is my main area of research at the University of Ottawa. So I look at the paleo records, and I look to see how quickly the temperature of our planet can change based in the past records. And I also look at the characteristics of the system change to see what's happening today. The whole hypothesis of my work is that we're undergoing early stages of abrupt climate change. So what does that mean? Well, there's been many periods in the Earth's history that we can glean from ice core records and sediment records that show that the temperature of the planet has increased 5 or 6 degrees within 1 decade or 2 decades. Okay? Not within 100 years, but within 1 or 2 decades. During the Ice Age period, between about 70 and 40,000 years ago, the temperature rose over Greenland 5 or 6 degrees in a decade or two, about 30 times. In fact, the largest temperature excursion was 16 degrees Celsius. Going back further, in the sediment records about 55 million years ago, the Earth was very warm, and the temperature rose globally by 5 degrees Celsius in 13 years, as shown in a very interesting Varves sediment sample. So if this happens, obviously things change very rapidly. Let's look at sea level rise quickly. I don't understand why people don't come to a common sense view on sea level rise. Why should we believe the currently accepted sea level rise of science? Because every few years that sea level rise number goes up. In fact, the doubling period of melt from Greenland and Antarctica ice caps, the rate of change of melting doubles every 7 years. This has gone on for about at least over 3 doubling periods, over 20 years. So if you just continue this doubling trend of 7 years, then we're talking about sea level rise of something like 7 meters by 2070. Okay, huge rises. So what are we going to do? We have to cut this vicious cycle of warming. So what we're proposing, and John's talked about, and Stuart's talked about, is interventions. We have to slash emissions. There's no question. We have to slash CO2 emissions, and quickly. But that's not sufficient. We also have to try to cool the Arctic, and we also have to try to actively remove CO2 from the atmosphere to head back down to a safer level. So there's technologies called solar radiation management, where you block some of the incoming light to cause cooling. That's a stopgap measure to get rapid cooling to allow the slashing of emissions. And John talked about the sea salt spraying from Salter. There's also something I coined anthropogenic Arctic volcano. I won't talk about that. There's all kinds of different ideas. But these methods do not address ocean acidification. The only way we can address ocean acidification is to remove the CO2 from the atmosphere by so-called CDR, or carbon dioxide removal methods. So we need to slash emissions. We need to reduce the CO2. So how do we do that? Well, we know that vegetation removes CO2. So we need to stop cutting down vegetation. We need to start increasing vegetation to absorb more CO2. We can also increase algae levels. Phytoplankton levels in the ocean have dropped something like 30% in 3 or 4 decades because the ocean's warming. It's becoming more stratified, so there's less uprising of nutrients, there's less vertical mixing, and there's less algae. So we need to address problems like that. And there's a big method that looks very promising, and it has to do with the soils. So the method is to hydrolyze carbon and bury it in the soil. And it makes the soil, it increases the nutrients in the soil, but it also captures the carbon and it's stored in the soil. So by changing farming practices and changing forestry practices using biochar, we can extract a lot of CO2 from the atmosphere. So I'm going to pass it over to Stuart, who's going to talk a little bit about that via a video.
I'm going to introduce another scientist, Dr. Johannes Lehmann. He's with Cornell University. He teaches in the College of Agriculture and Life Science. and he is the world's foremost authority on something called biochar, which is a carbon-negative soft technology. It does not take equipment so much as it takes doing, and doing broadly. It can be implemented in the household. It can be implemented at a community level. It can be implemented at a massive industrial level. Now, here's the words of Dr. Johannes.
Hello, I'm Johannes Lehmann, Professor of Soil Science at Cornell University. I'm so pleased to address you at a moment where the bilateral agreement on greenhouse gas emission reductions between the US and China has sent a clear signal for action. Specifically today, on World Soil Day, December 5, which kicks off the United Nations International Year of Soils 2015, I'm eager to discuss with you where soil fits into a comprehensive strategy to mitigate climate change. The science is absolutely clear. The global climate is changing faster than anticipated, and we have to do something about it. The silver bullet will prove elusive, and only a concerted international effort will provide us with a chance to mitigate and adapt to climate change by building a deep toolbox of approaches to reducing greenhouse gas emissions. But it is increasingly becoming clear that reducing emissions alone, while an indispensable prerequisite of any successful mitigation strategy, will not be sufficient, and an active withdrawal of atmospheric carbon dioxide will need to be part of managing climate change through, for example, carbon sequestration. I share the concern expressed by progressive thinkers that a scenario where we are forced to take drastic steps may prove disastrous without having done due diligence on the risks and opportunities of a portfolio of sequestration options. This year's IPCC report made impressive progress in laying out the need for carbon sequestration and provided the first data on what efforts are needed to reduce atmospheric carbon dioxide. The principal pathway to achieving this carbon drawdown put forward in the report is bioenergy with carbon capture and sequestration, or BECCS. The technical feasibility and cost-effective deployment are still not proven. Pilot projects should be put on the road without further delay. However, additional avenues must be explored. Pyrolysis bioenergy with biochar return to agricultural soils is a technically feasible approach to start sequestering carbon dioxide now, with little development time to initial deployment needed in comparison to BECCS. Such a strategy would not only remove carbon dioxide from the atmosphere, but also be able to restore soil health and increase crop productivity in degraded areas. Applying stringent sustainability criteria to biomass use yields a potential to withdraw 1 gigaton carbon per year from the atmosphere over the coming 100 years using biochar sequestration, with more being possible and less being likely given financial constraints. This may prove the stopgap measure that will allow a safe transition to a low or no emission society. There will be trade-offs between maximizing energy generation by using biomass and sequestering carbon with biochar. This must be stated very clearly. Opportunities and constraints have to be investigated now to be ready when far-reaching decisions about a comprehensive global strategy to carbon sequestration are made. The costs must be evaluated at scale of implementation with a clear pathway to crop yield increases by biochar addition to soil. Which brings me back to my point from the beginning. Do we want to utilize biomass only for energy, or rather a sustainability package that helps transition into climate-smart agriculture? Restoring and maintaining healthy and productive soils should, in my view, be prioritized, especially if it generates the same climate benefits at comparable costs. Thank you for your attention, and a happy World Soil Day.
That was, again, Dr. Johannes Lehmann. I thought it was very serendipitous. I did not realize that we were doing this press conference on World Soil Day. the beginning of a whole year being celebrated by the United Nations. Let me amplify for those of you who have not heard of biochar some of the things that he referred to but didn't spell out. Biochar is when you don't burn biomass, whether it be wood chips or cow dung or grass or any of the various forms of things that people burn to cook their dinners, to make steam when we got started in this whole thing. Instead of burning, which liberates the carbon into CO2, you pyrolyze it. You heat it and it outgasses. And then the gases can be burned and the charcoal, the char, remains. And it has a microscopic sponge-like consistency, which when buried in the soil, you fragment it, you powder it, and you bury it in the soil. It augments the fertility of the soil. You know, in water filtration, they use activated charcoal because it pulls impurities out of the water. Well, those impurities are nutrients to the plants. And they become very available because of carbon's ability to hold on to things like nitrogen and phosphorus and potassium, and to let go of them to things that want them. And so the soil roots grow into the biochar, and it is found to be an enhancement, not a fertilizer, but an enhancement to the fertility of soil, up to 10% of the volume of soil. And above that, I think you reach the diminishing returns. Now, we're close to the end of our time. Again, my name is Stuart Scott, and if you have any further questions, we did not allow time for questions in this session, but we will remain outside afterward if you have questions. I want to call attention to two things, however. We will, due to popular demand, we will repeat a lot of the substance of this presentation tomorrow at noon again. And for those of you who came in late, you missed some of the strongest information. So I encourage you to come back, and I encourage everyone to send other people back. People say I should have done a side event, which is more instructional, but I did it as a press conference. But we are here to be informative. And at 2 o'clock this afternoon, we will have what the UN calls an action. Our polar bear friend will be actively assisting us in the action, which is done in the area in the center of, shall we call this the campus, outside of the C building at 2 o'clock today. So please, that should be a lot of fun from 2 to 2:45. Bring your friends and join us tomorrow if you can. Thank you very much.